Well, welcome to another exciting episode of AP Chemistry here at Spain Park High School. Today is April the, what day?
20th.
20th?
It's 420.
Oh, Lord. You guys got to go home and do chemistry. And so, in a good sense. Anyway, so, once again, if you are enjoying these exciting AP Chemistry videos, feel free to subscribe to my channel and hit that like button. All right. So, in our lab, we did a titration. And we were using pretty potently poisonous purple potassium permanganate. Okay? Now, in that lab, what was cameraman, what was the purpose of the lab? Okay. The green stuff. Okay. The technical purpose is to determine the percent purity of our potassium trisoxylatofferrate 3 trihydrate crystals by titrating it with a standardized solution of pretty potently poisonous purple potassium permanganate. That's our purpose. But let's just kind of shortcut that. Our purpose is to determine the percent purity. Okay? Now, first off, our green crystals. What are they theoretically? What's the formula? Okay, so it's potassium trisoxylatofferrate 3 trihydrate. Okay, but if I'm saying percent purity, what does that imply if I'm trying to calculate percent purity?
It's not pure.
It may not be all pure. So how do I calculate percent purity? What over what? Part over the whole, okay? So we weighed out 0.1 grams. Okay? Of our green stuff. Is that the part or is that the whole? That's the whole, right? So we had 0.1 grams of the green crystals, or a 0.1 gram sample. Well, we're going to have to calculate everything, so you can write down whatever you want to write down, but you're going to need to know everything that I'm talking about. Okay? So I have 0.1 gram of a sample. But, what am I trying to find out on this? How much is actually this stuff? So how did we do that? We titrated it with the MnO4. Now, we skipped part A. Part A was to standardize the potassium permanganate solution. What does that mean, first off, to have a standardize or to have a standard solution? You know the concentration exactly. Okay? Now, this right here, we talked about this. Okay, Otto, stay with me. Come on. We talked about this, okay, on Monday, right before the lab. But this is our purple stuff. Now we're just having a net ionic equation, so we're leaving off the K. So what was the oxidation state of the manganese in the MnO4? Plus 7. How did we get that? What do we know oxygen is? Sam, go ahead. Oxygen's -2, so? So? How do I know that it's -1? Because the charge. If it's a compound like CO2, what's it going to add up to? 0. But if it's an ion, like oxalate, what are the charges going to add up to? -2. So I know it's going to equal -1. So therefore manganese must be +7. But now it's going to this colorless Mn2+. So what's happening to the manganese? Oxidized or reduced? Did the charge go up or charge go down? Went from 7 to 2. Okay? Again, let's think hard here. It went from 7 to 2, so did the number get bigger or smaller? Okay? It's got reduced. Gain electrons. Another way you can see. Notice it's saying plus 5 electrons. I'm adding 5 electrons. Leo goes Ger. Loss of electrons is oxidation. Gain of electrons is reduction. Right? I'm gaining electrons, so it's being reduced. It's gaining 5 electrons. So what's the oxidation state of carbon in C2O4? +3. Oxygen is -2. There's 4 of them. -8. It has to add up to the charge of -2. So the total positive is +6, but there's 2 of them. So each carbon is +3, and the oxidation state is always per individual atom. What is it in CO2? Oxygen is what? -2. There's 2 of them. -4, but this time it adds up to 0. So it's +4. This doesn't have any effect on it. So what's happening to the carbon? Let me give you a clue. If one thing is reduced, the other thing is oxidized. That's why we call it a redox reaction. A red ox. Okay, it's related to Paul Bunyan. It's his brother. Paul Bunyan was all about the blue ox. And he all read Paul Bunyan? Never read Paul Bunyan? Okay. All right. Somebody is literate in here. Somebody. Okay. So, this is oxidized. Okay? Yeah. Working on the train. All right. Working on the railroad, actually. So, this is oxidized. Now notice each carbon is going from +3 to +4. But we have 2 of them, so the total is 2 electrons. Notice the electrons here are on the opposite side. The electrons are being separated from it. It's losing the 2 electrons. Oxidation, the electrons are going to be a product. Reduction, the electrons are going to be a reactant. You're adding electrons, losing electrons. But electrons gained always has to equal electrons lost. So what did they have to do to get, when you add these 2 equations, what do we have to do to make these 2 equal? We had to multiply this one by 2 and this one by 5, right? Because electrons gained has to equal electrons lost. In a redox reaction, we not only have to balance atoms, we have to make sure we balance electrons as well, balance charge. And the key is always going to be electrons gained has to equal electrons lost. You just cross multiply. So, this was the part that we skipped. Okay? We would have, in part A, we have this equation right here. We needed to determine the exact concentration. To standardize a solution means to determine the concentration exactly. So part A says to measure 0.12 to 0.17. So let's just say we put 0.15 grams of the potassium oxalate. K2C2O4 is what we would have measured in. Because you can't just go buy oxalate ion at the store. It's going to be with something. So we would have measured 0.15 grams of potassium oxalate and done the exact same thing. Dissolved it in acid to acidify the solution. Because these redox, it helps with the electrons being transferred, and they do different things, whether it's an acidic or basic solution. And so we acidified the solution, so we dissolved it in H2SO4. All All right? So if I know exact number of grams, and by the way, what is molarity? What are the units on molarity? Moles over liters. So I can take grams divided by the molar mass to get moles, use my balanced equation to get moles. So I would have moles of KMnO4. Where do I get liters from? The titrate. I read it from my burette. So I would have had my flask, I would have had my 0.15 grams. Again, it wouldn't matter how much acid I added because that's not going to change how many moles of this I have. Okay, it's just going to dilute it and let them, dissociate the ions and all that. Okay, so then I titrate in my KMnO4. Now again, I'm leaving off the K because it's a spectator ion, so I'm just MnO4. So if I know grams, as soon as one drop, what's the color change gonna? What was it? Turned purple or pink, right? Because what did that imply? Why? This is purple. This is colorless. Why did it go purple?
It's not reacting.
So what?
It's not reacting.
With?
With the C2O1.
This is all gone. As long as you're adding this, as long as there's some of this, it reacted, the purple went away and went colorless. It got reduced. As long as we had some of this kept getting reduced to that. But as soon as this was used up, one extra drop of our pretty potent poisonous purple potassium permanganate, one extra drop caused it to stay pink. We wanted it to just be one drop difference. Then I know that very close, we're in the exact no limiting reactant, they're exact mole ratios, right? You following me? So, mass, use the molar mass to go to moles, and then however many milliliters it took to do that, we're going to say that many moles must have been in this volume. So we get moles per liter. And we would have done that 3 times. Measuring out potassium oxalate, 0.15 grams, somewhere in that range, 3 times, just like we did with the green crystal. That would have standardized my KMnO4. We didn't have time for that. Instead, we had a standardized solution, and we know it was standardized because I made it. So we know it's exact. Okay? Because I'm a trained professional. Okay? But I did measure it exactly 1.58 grams. I used a 1 liter volumetric flask. I measured it in there, I added it up, dissolved it, and then filled it up to where the bottom of the meniscus was right on that 1 liter line. Okay? However, KMnO4 is really not what we call a primary standard. It does tend to react a little bit with the water, produce a little CO2. It reacts actually with the CO2 that's in the water, and it's not perfectly pure. We didn't have time to standardize it. But when we do standardize it, it usually would come out to 0.0096, 0.0097 to 2 sig figs. We're just going to have to deal with it. So we're going to say that our standardized solution was 0.010 molar, and you all recorded that in your data somewhere. Okay? But that's what we were supposed to do in the first part. Now, what we actually did is we turned the page. Little Bob Seger, turn the page. Anybody classic rock fan? Okay? All right, so this is the net ionic of our green stuff. Our green crystal, we're taking the potassium off. When you put this into water, it dissociates, the potassium breaks free, the water breaks free, becomes part of the water that's in there. And so we have potassium ions and this complex tris oxalato ferrate 3. Where's the 3 coming from? Okay, very good, Sam. Woo! Throwing that out. Come on, all-star. Okay. Now let's talk about how we can figure that out. Okay. What's the charge on oxalate? Bottom. Try again. Bottom of the third column. -2. But we have 3 of them. So it's -6. Okay? This is +1, so it's +3. So the water is 0. So therefore, to make this all add up, iron must be +3. Okay? So the iron is +3. So that's the tris oxalato, the oxalate ion, tris oxalato, ferrate, okay? The ferric, we're going to ferrate 3 trihydrate. But we don't care about the potassium or the water. Now the reality is we really don't care about the iron because iron's still +3 here too. It's just attached, we call this a complex ion, okay? And so we just have this ion reacting, the iron just breaks free. It's really the oxalate, just like the other part, just like equation 8, the oxalate is really what's being changed. The carbon is going from +3 to +4. Okay? But now we have 6 electrons. Now the manganese is doing the exact same reaction as it was previously. MnO4 plus 5 electrons plus 8 H pluses goes to Mn2 plus 4 waters. Right? So this is the reduction half reaction. This is now our oxidation half reaction. So what do I have to do to this to balance when I want to add those two together? How do I get this? Multiply the top one. I need to multiply this one by 6 and this one by 5, right? So I'm going to get 6, 30, 48, 6, and 24. Now I'm going to get 5, 5, 30, and 30. Now it's these that are most important. That has to match up. When you balance a redox, electrons gained has to equal electrons lost. Okay? Electrons gained has to equal electrons lost. Now, normally, if there's some H pluses over here and some waters over here, you're going to cancel them out and go net, just like adding 2 equations together. You guys know how to do that. This one, there aren't anything else, just the electrons cancel. So my balanced equation is 6 MnO4 minuses plus 5 Fe C2O4 3 minuses plus 48 H pluses goes to 6 Mn2 pluses plus 30 CO2s plus 24 H2Os. That's the net ionic equation for the reaction that we just did. I'm working up a sweat. Just in the nick of time. Well, we're 2 spheres down. No wonder I'm hot. All right, so we're coming back to this. We're coming back to our ultimate goal. So now we have a balanced equation. Part A, the part we didn't do, we knew the oxalate. We were looking for how much KMnO4. What was the concentration of my KMnO4? We were standardizing that. This time now, I know that this is exactly 0.010 molar. Right? What's my goal? What do I need to find out? Which means I am looking for X grams of K3 Fe C2O4 3.3H2Os. That's what I'm looking for. Then it'll be times 100. So I need to know this. So what did I measure? What's the one thing we measured in our lab? Milliliters of this. Well, if I know milliliters of this and I know the molarity of that, what do I really know? I know moles. Molarity times volume equals moles. So right when it turned faint pink, where one drop made a change, what did that mean? All of that was used up, right? So we're in exact mole ratios, which means for every 6 moles of this that I put in, that I measured, molarity times volume, for every 6, there must have been 5 moles of that. But I don't want moles, I want grams. So, now do I just use this? Was the green crystal just this? What was the green crystal? That. Which we measured at one of the first labs to be 491 grams per mole. Okay? Because that's not what we put in. We're measuring the purity of the whole thing, not just the one ion. The solid was this. We're just doing the net ionic. We're just getting rid of all the spectators here. All right? So we can take volume times molarity to get moles to grams, and we get percent purity. We did it 3 times. So calculate your percent purity 3 times and get an average. Now y'all, I'm going to break my cardinal rule. This is homework and it's going to be due on Monday. Today's Thursday. Okay? That's all you have to do though. You only have to calculate your percent purity 3 times and then get the average. And that's what you're going to say the purity is. Now look. In a utopian world, what should the numerator come out to? 0.1. If it was impure, if say some KCl got trapped, some of the byproduct from the very first reaction, and we talked about that, KCl got trapped in it. Well, then that KCl is going to be spectator in all here. It's not going to be reduced or oxidized. So it was just extra weight in our 0.1 gram. So only maybe 0.095 grams was actually potassium tricycloalpha 3 trihydrate. We had some other impurities in there. How could we explain if you get 110%? What's the most probable?
Oh, you went not enough.
Put too much titration.
Okay, you put too much titrant, and the titrant is the titrant the stuff in the flask or the burette? Burette. Okay, because that's the only thing you measured, right? Because it's molarity, it's standard. I made it, so that's not wrong. Okay, molarity times volume. If this volume is too big, what does that mean about moles? Moles, because molarity times volume is equal to moles. So if the volume's too big, moles is too big. If moles of this is too big, what does that mean about moles of that? Because we're still multiplying. And if moles of this is too big, what does that mean about grams of this? Too big, because we're still multiplying. If anything you measure is in the denominator, and you go too big, it's going to make the answer too small. So you just got to follow the mistake. Since this is the only thing we're measuring, how does changing that affect it? Now, what happens if your burette, you walk into the lab and the previous class drained out all the KMnO4 and had rinsed it with water, and then you just filled it up with KMnO4? What's that going to do to your KMnO4? Diluted. So what's that going to mean about the amount that you would use? Take more or less? It's going to take more, right? So your first trial maybe take way more, not way more, but enough more to make a lab question out of it on an AP test. Okay? It's going to make you use more. So would that be an excuse to have a 95% purity? No, that's going to be to have 105%, right? It's not going to explain why you're too little. It's going to cause you to be too much. So you got to think about how is the error going to affect your final result. You with me?
Yes.
Okay. Get to do that at home. All right. So let's put this away so you're not tempted to do it now. Although Zach's working diligently. Okay, hey, make it neat. You need to have your data table, you need to have your observations for each trial, and you need to have your calculations. And if you want bonus, you can put the purpose as I stated it. Sam, write it down. I'm gonna state it again. I already stated it. You gotta try and figure out. Hey, you're gonna have to go back and watch the video. Hey, and hit the like button.
Wait, so if we go back and subscribe to the video, we get bonus points?
No, you got to put that whole purpose down on top of your lab report.
Oh, we should. I don't have any roll. I put it two.
There's not enough lines on my paper for that.
You being so serious.
Okay.
Like 3 lines.
You're being like 100% serious about the bonus. I would be sitting through this.
I am not being serious about the bonus. Don't go back. Hey, there's too much to do. You guys have too much to do in this next week to do something like that.
He's gonna have fun watching
Maybe
this.
worth it for like the 5 seconds in between.
All right. We have, what, 52, right?
Yep.
Got the rest of today and all of tomorrow to do electrochemistry. Okay, let's go. We can do it. All right, electrochemistry. First off, hey, let's break it down. Electrochemistry. Okay, electricity and chemistry. How do we produce electricity? What's the effect of electricity on a chemical reaction? So the first thing we're going to look at, we're going to go 2 ways. We're going to first, how do we make electricity from a chemical reaction? And then the second thing, which we're going to look at for maybe 10 minutes hopefully, is what happens to a reaction when you put electricity in. Okay? So we got to be able to go, what allows us to get electricity out? And we call that a battery. Okay? And a battery is going to be called either a voltaic cell or a galvanic cell. And I look it up every year. Sometimes it's called a Daniel cell, but so I sometimes think that it's called, his last name is Galvani. So galvanic cell is an Italian guy. But I really think his name is Luigi. Luigi Galvani. Okay? And I look it up every year and I always forget, and I don't have time to look it up today. So if you're watching this somewhere across the world and I'm wrong, I'm sorry, you can look it up. Ask Chatbot or whatever that, you know. Yeah, that guy, you know, or girl, whoever the robot, whoever the robot is. Okay. So, a voltaic cell, it's a chemical reaction between 2 metals, okay, or 2 substances, one gaining, one losing, one being oxidized, one being reduced, okay? So I have over here, ooh. Okay? I have 2 metals put into a solution. I have some copper metal put into some copper sulfate, and I have some lead metal put into some lead nitrate. And I have them hooked up to a voltmeter. Now, Again, I'm going to ask you, you don't have to follow me, I'm going to ask you a very deep question here. What do you think a voltmeter measures? Okay, measures volts. It does not supply power. It just simply measures volts. Now let me tell you just a little bit about electricity. Okay? Electricity is like water flowing through a hose. You're good. There you go. The electrons are the water flowing through a wire. Okay? So your current is how many electrons are flowing through your wire. What's the rate at which they're flowing through? It's measured in amperes, which is abbreviated amps. So many amps, a 15 amp circuit, a 30 amp circuit. Okay, it's an A with a little halo on top of the A as the symbol for an amp. It's the flow of electrons through the wire. And electrons have a charge, so we measure the flow in terms of what's the actual charge flowing through the wire, coulombs, and we're going to talk about that, how many coulombs per second are flowing through. That's your current. The voltage is the pressure. Somebody called, text message. Okay, so the voltage is the pressure pushing it. It's like a fireman's hose. Okay, you can have at your house, you can have, you know, if anybody is using water, my kitchen sink is like barely a dribble. Okay, water's coming out. There's electrons flowing through the wire, but the pressure, the voltage behind it, the water pressure is very low. Now, I have a pressure washer. So I can crank my pressure washer up and a little bit leaks out the end because it's not a perfect seal. So my current is real low, but the pressure inside the hose is very high, 2400 PSI. Okay? So that's my voltage. What's the push of the electrons? It's sometimes called the EMF, the electromotive force. What's the force pushing the electrons through? That's your voltage. Okay? So we can measure, a voltmeter measures that volts. What's the pressure? And the pressure is going to be measured by the difference between how much does this one want electrons versus how much does this element want electrons. So everybody turn to page 1105 in your textbook and you'll see a table of reduction potentials. 1105. Okay, and on page 1105, look for copper 2+. Now there's several of them. There's like 3 of them for copper. It's copper 2+ plus 1 electron going to copper plus, copper 1+ plus an electron going to copper solid, and copper 2+ plus 2 electrons going to copper solid. We want copper 2+ plus 2 electrons going to copper solid. What does it say the E cell is? Not E, just the E red on this one is actually 0.337, and it's positive. Okay, that's its reduction potential. What is it for lead? It's negative 0.126 volts. So they have different reduction potentials. Again, remember, reduction is the gain of electrons. Notice everything on that table, it's plus electrons. Electrons are all on the reactant side. Everything is written as a reduction potential. But some things want electrons more than others. Some things have a greater reduction potential than others. So which one do you think wins? Reduction is gain of electrons. Which one gets the electrons? Why? It's got a greater, more positive reduction potential. It's got a greater attraction for the electrons than the lead does. So the lead actually is going to go this way. The lead, because I have in my solutions over here, I have copper metal, copper sulfate, lead, metal, lead nitrate. So I have Pb plus 2 in solution and Pb solid. I have Cu solid and Cu2 plus in solution. So we can determine which one is going to get reduced. The one that's going to get the electrons is the copper because it's got that more positive reduction potential. Now these numbers are always going to be given to you in the problem.
What is the red?
Reduction. It's the reduction potential. Everything that, notice what's it say at the top of the chart?
Standard reduction.
Standard reduction potentials. They're not giving you the oxidation potential. But here's the deal. The oxidation potential is the reverse. You just go the other direction. You just play the movie backwards. So lead's oxidation potential is lead going to Pb2 plus 2 electrons. And you would just swap the sign. But we can get the voltage of this battery that we're going to make is that we can say that E cell, okay, my battery is going to equal E red minus E ox. E red minus E ox. The thing that's getting reduced, well, which one of these two things do we say is getting reduced?
Copper.
The copper. So it's going to equal the 0.337 minus the E ox, which is negative 0.126. So I'm going to add those together and I'm going to get 0.463. That's the voltage of my battery. Okay? Now, some books, look, some books say E red plus E ox. But if you do that, if you do plus, you have to change this sign on your own because the oxidation is going to be the reverse of this. If the reduction potential is negative 0.126, lead's oxidation potential is positive 0.126, going the other direction. Okay? But when you put a negative here, that automatically changes the sign for me. So we're just always going to use E red minus E ox. You don't change the sign, you just, whatever's in there, this negative changes the sign for you. So whatever's in the book, whatever's in the problem, that's the value you put in. You don't change signs. The other good thing is, now when I add these two equations together, my net result is, and I'm just going to go up here just for the sake of space so I don't erase anything, okay? This is getting reduced, this is getting oxidized, so I'm going to say Cu2 plus aqueous is reacting with the lead solid, and it's going to make Cu solid plus Pb2 plus aqueous. This is going in reverse because it's getting oxidized. The thing that's the lesser oxidation, the lesser reduction potential is the one that's going to get oxidized. It's going to go in the reverse direction. Okay? So it's, now, if there happened to be a 2 and a 3 here, this is the good thing. It's an intrinsic property. It doesn't matter. You don't have to multiply by anything. It's always just red minus ox. Okay? The battery cell, doesn't matter what the coefficients are, you just always E red minus E ox, whatever the values are, it doesn't matter the coefficients. Okay? So it's a super simple calculation. There was one that was like this, kind of on the mock exam that you guys didn't know how to do just because we hadn't got there yet, but it was just E red minus E ox. So that means that the reality is that in this reaction, the copper is stealing electrons. 2 electrons are being transferred from the lead to the copper. So at my electrode, the copper is precipitating out. The Cu2 plus is turning into copper on the metal surface. And the lead is going from lead to Pb2 plus. It's going from solid to aqueous. It's dissolving here. But what's my voltmeter measuring? I know, but how much? Oh, no, that's what it's supposed to. What's it actually measuring? It looks like 0 to me.
Because there's not a current right there.
Why isn't there a current?
We don't have a source.
Well, we're making the source, we're making the battery, we're saying it should be producing this voltage.
It's not connected.
But it's not connected.
Okay, you guys are really warm. Tell me, what do you mean it's not connected? I got this is connected to the voltmeter, this is connected to the voltmeter.
It's not a full circuit.
Where are we missing the circuit? Between these two, right? Okay, the circuit's not complete. Somehow I have to get it connected. Now, if I just put this copper, well actually the lead, into the copper right here, the reaction would just take place and we wouldn't be able to harness it. We want the electrons to go externally so we can make them do work, a flow of electricity, we can use it, make the battery. So I need what's called a salt bridge. It's very fancy. It's a paper towel that's been soaking in potassium nitrate. Potassium and nitrate are almost always spectator ions. They don't do anything, but they're positive and they're negative. Okay? Because right now, if electrons begin to flow, they want to flow, just stay. They want to flow from the lead to the copper, but as soon as they start building up on the copper, now we're going to have negative charge in here, and it stops and resists everything. So we have to let the whole circuit, let it flow. So I take my paper towel, twist it up. A real one has a little bit fancier, but hey, we'll MacGyver it. You guys don't know who MacGyver is. So now I put that in. Now you can see it jumps to here almost to, it's between, here's the 0.5 right there. So it's just a little bit less than 0.5. Okay? Good save. Now, listen, we've created a battery. Now the little degree symbol means standard conditions. Standard conditions means everything's 1 molar. I just mixed those together. I didn't make them 1 molar, I just dumped some stuff in there because I was in a hurry. Okay, so we may not get exactly what the 0.463, but it's pretty close actually, okay, to the voltage that battery can give. All right, so we can look at this and we can always find the cell potential just by looking at our table, E red minus E ox. In every redox reaction, one thing gets oxidized, one thing gets reduced. The thing with the greater reduction potential is the one that's going to get reduced. And it's just E red minus E ox. That's going to be your cell potential. Now, interesting fact, all batteries, D, C, I don't know what happened to B, AA, AAA, they all have the exact same material on the inside. They're all the exact same voltage, somewhere around 1.5. They actually come out to about 1.62 when they're fresh. So what's going to be the difference, you think, in the batteries? The amount. Okay, because the electrons are going to flow. They're going to go flow from the, hey, and by the way, it always goes, okay, it's flowing, by definition, cathode is where reduction takes place. The anode is where oxidation takes place. And you can remember that because the vowels stay together and the consonants stay together. C and R, A and O. Okay? So notice the source, the lead is getting oxidized. That's the source of the electrons. So the electrons are flowing from the anode, where oxidation is occurring, to the cathode. So the electrons here are flowing this way.
It's always negative, positive.
It's always anode to cathode. It always goes from, this is the source of the electrons, this is the recipient of the electrons. This is losing, this is gaining. It's going from the anode to the cathode. Now, the last thing, how do we know that the battery is, how do I know how to build a battery? How do I know if it's going to work? How do I know if it's going to be spontaneous? What determines the spontaneity of a reaction? Delta G. Well, delta G is going to equal negative NFE. Okay? Now, I'm going to talk about this more tomorrow because we're just about out of time, but let me just finish in the last few seconds. N is the number of moles being transferred. In our reaction here, how many moles are being transferred?
2 to 1.
2. 2 being gained, 2 being lost. in our balanced reaction of the lab that we did, how many electrons were being transferred? After we cross multiplied? 30. So N would have been 30. F is called a Faraday, it's a constant. But in order for delta G to be negative, what must be the sign of E? Positive. A positive E indicates a spontaneous reaction. And we're going to practice doing this equation tomorrow. All right, y'all have a great day.